I'm recording this. Are there any questions that anybody has?
Yes.
Yes.
On 3B, I just get stuck in this loop of going back to just like the original proof, and I don't know what I'm doing. I'm using identity.
B.
Yeah,
You keep going from this back to the same thing?
yeah, on B, just in like a different
Oh,
order.
on B.
Yeah,
We talked about this one last time, and I gave you a sequence. Or no, I had you started off. So the first thing to do on this one, let me give you guys another step on that one. So it's A or A and B. So 3B. So start off like this. So hint. I mean, not that there aren't other ways to do it, but here's one way. A or A and B, or A and B naught. Right, and the goal is da 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 all the way down to A. Right, so this whole thing should simplify to just A. All right, so start off with distribution. Well, start off with association. Before you do distribution, it might be a good idea to do association. Associate the two if you need to. I mean, if it's a conjunction of more than two terms, or disjunction of more than two terms, and you want to do distribution, you might want to associate them together like that. The reason being, I mean, you don't strictly have to do it, but afterwards, after you apply distribution, that parentheses has to be there. Because if you don't, then you'll have stuff like this: P or Q and R. P or Q and R, and that just doesn't, it's ambiguous, like we've been talking about. So distribution. So I'm going to distribute the A or over the A and B. So then that becomes what? A or A and A and B, or A or B. Right? A or A and A or B. Or A and B. Okay, we didn't do anything with that term yet. And then from here, use idempotent. Idempotent is that A or A is the same as A. Right, so this becomes A and A or B. Or A and B not. Okay, so from here, now this may be, let me write this bigger. The way in which you write things often has some bearing on how well you sort of perceive what's going on. So this is of the form, so this is like A and Q, or A and R, right? Where this is Q and this is R. So now you want to use distribution again in reverse. Okay, we want to use distribution in reverse here to factor out the A and. right? This is A and Q, or A and R. Now, when you use distribution on that, excuse me, this becomes A and Q or R, like that. What you don't want to do, I think maybe what you were doing was distributing this through here, A and A or A and B, and which gets you back to that. Or not that, but it gets you back to something similar to that. So that's the next step you want. Okay, but don't use Q. Don't use the letter Q. Don't use the letter R. Q is this thing. R is this thing. But since they're not just one symbol, the Q and R aren't just one symbol. Maybe it threw you off a little bit. All right, so that's step one. That's step two. This is step three, and then from there, should be able to work it out. Anybody else?
I'm stuck on 3A.
3A. So 3A, that's that one. That's called the exportation rule. And so 3A, you have A implies B implies C, and you want that to be equivalent to A and B implies C. So with this one, I'll even just tell you the first few steps. So first, use implication twice. Right, to change the implications to disjunctions. All right, use implication twice. So A implies B implies C. So implication twice. So the B implies C and the A implies whatever. This becomes A naught or B naught or C. Did you get that?
Yeah, I got that far, and then I did associative.
Sure, then what?
And then I think it might be De Morgan's, but
De
I'm not
Morgan's,
positive.
yep. In reverse, De Morgan. Yeah, and then implication again. That would be the answer you're looking for.
Okay.
All right. Which is this one? Make sure your application of De Morgan is correct. So associative, this becomes A naught or B naught or C. Okay, so that's the first two steps. What else, guys?
Um, 4E I was also struggling on.
4E. And B, you mean? Or, that's the wrong one. That was assignment 2, by the way. I was just looking at there. That's assignment 2. I still need to make up a final problem on that one. But the first 3 are done. I just need to make up a fourth. But that'll be posted after class. Then that'll be due in 2 weeks. So Wednesday and 2 weeks from now, which is the 10th. So for E.
Yeah.
For E, if the file is not damaged, and the processor is fast, and the printer is slow. So for E, so if the file is not damaged, and the processor is fast, then the printer is slow. So if the file is not damaged and the printer is fast, then, not what they were. If the file is not damaged and the processor is fast, then the printer is slow. So you want to take that whole thing there and negate it. Right, now what is the negation of a implication? What is the negation of an implication, right? We've been talking about that a few times, right? Yeah, P implies Q. And you want to negate that. Right, what's the negation of that?
You'd have to use implication and then De Morgan.
Sure, yeah. So the steps are, first do the implication tautology, which is P naught or Q. And then De Morgan plus double negation, you get P and Q naught. Right, it's P naught, or Q naught, Q naught. And then that's just P. Alright, so that's something to remember, that if P then Q, if you want to negate it, is P and Q naught. Okay, that's definitely something to remember. I mean, that's the steps of the named tautologies, but that's still just some rule that you want to remember. P implies Q negated is P and Q. Essentially, the only time an implication is false, when the hypothesis is true and the conclusion is false, right? All right, so here, this becomes what?
So you would put parentheses around both not D and F implies not S.
Oh, right, but I want to negate it. Like, that's the hypothesis, so I put it here. Right, so P implies Q negated is the hypothesis, conjunction, conclusion negated. Right? Hypothesis, conjunction, conclusion negated. So what do I have here?
Not D naught and F or Q.
Q.
Or I'm sorry, S.
Yeah. Well, what's the connector?
Or and.
And. Yeah. Right, and via associative, you can just write it D and not and F and S. Right. So the file is damaged, comma, the processor is fast, comma, negated, comma, and the printer is not slow. Is that clear? How that negation happens? Right, and then we just need to write that back in English. All right, so is that clear? I don't know who was that asked me the question, but is that clear? Or does that help? Or not?
I think so. So the only thing that would really be negated in the actual sentence is the last part.
Right, but the connector changed. Right, it's no longer implication; it's just conjunction.
Gotcha. Thank you.
Mm-hmm. So, for example, if you want to negate, if it swims, then it's a fish. If it swims, then it's a fish. Negated is, right, it swims and it is not a fish. Right? You have the hypothesis and you have the conclusion negated. Right? If it swims, then it's a fish. Not is it swims and it's not a fish. Instead of implies or if then, it's and. So what if we had something like this, right? If it swims or it has scales. If it swims or it has scales, then it's a fish. Right? How do we put that into propositional logic?
We can say S or F implies, or S or C implies F.
Yeah. W or C implies F, right? And then you want to negate it. Right? So this becomes, what's the symbolic form? What's the negation of this?
Would it be W or W naught or C and
Again, the negation of P implies Q is P and Q naught. The implication changes to conjunction. Right? The conclusion is negated, but the hypothesis is not.
Right.
Yeah. So this becomes.
So it'd be W or C and F naught.
Now, of course, I need to do what here? I can't write W or C and F naught. That's ambiguous. I need to do what?
Probably F naught and W or C.
I mean, I need to group it properly.
Oh, right. Parentheses.
Where?
Around W and C.
Right. Like here you don't need it because implication has lower precedence than disjunction. But when you change this to conjunction, disjunction no longer has precedence. So since it was first here, it's got to be first here. Anyway, so in English, so negated is, all right, so writing this in English is what?
If it swims.
No, there's no if. It's just ands and ors here.
Oh. I'm not sure.
So how do we write W or C? So W or C. So the main connector is the and. Right? So it's going to be something, and it's not a fish.
It swims and it has scales.
Or here, right?
Yeah. Or.
Yeah. So in other words, to make it sort of, you can just, I mean, it swims, or it has scales, and it's not a fish. This is ambiguous. In English, it's ambiguous. In order to show that this connection comes first and the and comes second, what could you do grammatically here?
You could put a comma.
You can put a comma. That's probably the you know the quickest way to do it, right? So it swims or it has scales, comma, and it's not a fish. Or you could say what? Give it a little more flair. One way to set off the or is with the word either, right? It either swims or it has scales. And then, a comma there is good if you want, but it's not a fish. And it's not a fish, but it's not a fish. However, it's not a fish. It either swims or it has scales, but golly gee, it's not a fish. It's all the same thing. All right, this is a little different than the example in the homework. In the homework, I had what here? Instead of an or there, it was what?
And.
It's an and, right? So in the end, the sentence is a little more complicated here because there's an or and an and, right? Or and. So you have to set off the connectors in some way. Here you don't have to. It's and, right? All right. So it's not a dump truck and it's not a fire truck, and right, it doesn't have a siren, something like that. You with me, everybody?
Yeah.
Hope folks have started the assignment, like at least already. If you haven't started already, please do. Okay. Again, the last minute doing of assignments just doesn't really. It's not going to work for you. It might work for the first couple, but it's not going to work in general. Right? Another thing that I kind of expect you to do is the following. I think I said it before, but let me say it again. I do lots of examples in class, right? Like I'll do an example and I'll work through it for you and get you an answer of some sort. When I do an example, you need to do that example as well. Okay, what you need to do is take the example and try to do it on your own without looking at how I did it. And then, go back and look at it again. Then go back and look at my solution and see if you got it the same. If you didn't get it the same, see where you went wrong and then do it again. So let me ask you a question. Don't answer me verbally. Do you do problems more than once? Are you the type of student that does a problem more than once? For sure if you get it wrong, but even if you get it right? Don't answer me. Just answer yourself. Are you the type of student that will do a problem more than once? I mean, not always, but some of the nicer, more meaty problems. Okay, you got to get in the habit of going over things more than once. Okay, if you haven't already, you need to, start doing it. Now, I know with my own kids from experience that, most students just don't naturally do that. But you need to start doing that. The point is to reach a full understanding of every example presented. A full understanding. So a full understanding is that you can do it on your own and you can explain what it is that you're doing. you need to reach that level of facility with the material. Okay. Any other questions? Anything else I can clear up on the assignment? Anything else, guys? All right. So I mean, we can ask again on Friday, but you can email me as well if you need to meet. We can always do that. All right. So back to chapter 2, predicate logic. So I've got an assignment for chapter 2 ready to go. Well, I'll finish it up after class. I just need to do a fourth problem here, and this will be gone. So that'll be due in 2 weeks. 2 weeks from today. We should go through this maybe a little faster, I think, than the first chapter. All right. So let's do a quick recap. So a predicate is a statement or a proposition, if you want to call it that, with a variable entry, and the predicate is not true or false until you somehow know something about the value of that variable entry. And you can change it, with different entries. It becomes different. So E of X is the statement X is even. Right? So E of 5 is even. That's false. E of 4 is 4 is even. That's false. E of the square root of 2, well, non-integers are neither even nor odd, so we just say false. You can have 2 variable entries instead of 1. SXY is the statement X plus Y equals 10. So S37 is true. S73 is not true. S44 is false. Or sorry, not true, is true. S37, S73, right? 3 plus 7 is 10, so is 7 plus 3, because addition is commutative. And S44, 4 plus 4 is not 10, it's 8. Not that you can always, have a commutative relationship here with 2 variable predicates. PXY is X is the parent of Y. So, right, if Doug is the father of Jake, is true, Doug is the parent of Jake. If that's true, then Jake is not the parent of Doug. Right? That's going to be false. All right. Other than just substituting values for the variables in a predicate, you can do, you do more often. You quantify variables over a domain. So a domain D of possible values. So there's universal quantification for every x. P of x means for all x, P of x, every x makes P of x true, or each x makes P of x true. For all x, P not x means no x makes P of x true, or every x makes P of x false. So universal quantification, every, each, all, these are all ways of doing universal quantification. And then this one, no x, that's universal quantification. Universal quantification of the negative. Right? I mean, if I say no horses are purple, what do I mean? I mean, all horses are not purple. Not some horses are not purple. All horses are not purple. No horses are purple. No baseballs are cubes. I mean, all baseballs are spheres. No baseballs are cubes. At least not one that I've ever seen. So formally, you say that for all x, P of x is true over domain D when P of x is true for any x chosen from the domain. So if D is the set of all horses and P of x is purple, then for all x, P of x is false. If D is the set of all candies, for all x, P of x is still false, because not all candies are purple. I keep this big purple kick here. I should let's get the different example here. Come on, erase. Or how about so D is equal to the set of all squirrels. The set of all squirrels. Right, and B of x is x has a bushy tail. And then for all x, B of x is true. I think it is anyway, right? Because for any squirrel that you pick, right, out of the domain, the set of all, for anything you pick out of the domain, some squirrel, that squirrel has a bushy tail. At least I think they do. Do they? Are there squirrels without bushy tails? Some weird species of squirrel I've never heard about. Some more examples here. For all x, x is bigger than 0. For all x, x is bigger than 0. So if the domain is the set 1, 2, 3, 4, 5, 6, 7, you know, the natural numbers as they're often called, then for all x, x bigger than 0, that's true. If you're talking about the set of all integers, you know, so that's all the positive integer whole numbers, negative whole numbers, and 0. For all x, x bigger than 0 is false, because there are some things that are not bigger than 0. And how about this one? So D is the set 0, 1, 2, 3, 4, 5, so on and so forth. For all x, x is bigger than 0. That's false. Where does it fail? Which x's are not bigger than 0 in this domain?
Zero.
Just 0. It just fails once. Okay, but that's enough to make the whole thing false. Okay, again, you know, in predicate logic, you know, or in logic in general, I mean, everything is completely literal. When we mean for all, we mean for all, not everybody except one. So, if depending on how far in life you go as a mathematician, this will this will affect your thinking. So whenever you hear people say, "Well, everybody likes chocolate," I always think to myself, "No, not everybody. Almost everybody, but not everybody." So people often say, "Well, everybody does this," or, you know, "This is always true." You know, when what they really mean is, well, you know, it's often true, you know, or it's usually true, or you know, the preponderance in the you know, vast number of cases, you know, it's true. But, you know, there are some small examples where it's not. But anyway, in math, even if there's just a couple examples of where it's untrue, you can't say it's always true. Second type of quantification is existential quantification. So there exists x, P of x means there is an x making P of x true, or some x makes P of x true, or at least one x makes P of x true. Formally, there exists x, P of x is true over domain D when there's at least one x in the domain. When P of x is true. One of them, two of them, infinitely many of them, or even all of them. So again, there exists x such that x is bigger than 0. Here, for this domain, 1, 2, 3, 4, 5, 6, 7, you know, like that, there's at least one x such that x is bigger than 0. That's true. What is also true is that for all x, x is bigger than 0. It doesn't make this one false. It just means it's not the whole story. Okay? There exists x such that x is bigger than 0. It's true here. There's infinitely many elements of that domain where x is bigger than 0. Here, there's only one element in the domain where x is bigger than 0. And here, there's nothing in the domain such that x is bigger than 0. We're just taking the negative integers there. -1, -2, -3, -4, so on and so forth. Stacking quantifiers together. So, for all x, there exists a y. Pxy means, in English, for every x in the domain, there is a y in the domain, which depends on x, making Pxy true. There exists x for all y, Pxy means there is one particular x in the domain, and that x for every y satisfies Pxy. So this x works universally for every y. Here, this y depends on which x you're talking about. So the standard examples of this, for every x, there exists a y such that x plus y is equal to 0. For every x, there exists a y such that x plus y equals 0. Here, in this domain, for any x you choose, like 3, right, there does exist a y, -3, dependent upon the x, whose sum goes to 0. Right? Or if I picked x equal to -28, then the y that goes along with it is 28. And then -28 plus 28 is equal to 0. So for every x, or like if I picked x equal to 0, then the y that I would pick to go along with the 0 is 0 itself, the same thing, and 0 plus 0 is 0. So it's true here. For any x you pick, the y that you want is the negative of x. Here it's false, because for any x you pick, that y that adds to 0 with it isn't there. Same thing here, it's again false. It is true in one instance with the 0. You know, if I picked x equal to 0, then you pick y equal to 0, and it's, you know, it adds to 0. But for anything else, I mean, if I picked x equal to 3, I don't have y equal to -3 in the domain to work with. So here it's false. All right, there exists an x such that for every y, x plus y is 0. This is false over this domain here. There is no one particular x that you add to any y to be equal to 0. Right? X plus y equal to 0, the y depends on the x, as they say. Right? So there's nothing I can pick here. If I picked x equal to 0, well, 0 plus y is not equal to 0. For every y. For some y's it is. For every y, you know. No. Can you think of a domain where this would be true? There is a domain where this does work. There is a domain that, you know, of within the integers that would make this true. There exists one particular x such that for every y, x plus y equals 0. There's one subset of D, of the integers, for which this statement would actually be true. So you want to see what it is? can you think of a domain within the set of integers for which there exists one special x such that for every y, x plus y equals 0. Anyway, so back to that in a moment. For every x, there exists a y such that x times y is equal to 0. Sure. Which y would you pick? Y equal to 0. 0 times whatever is 0. So, as a matter of fact, the stronger statement, there exists one universal x. There exists one x such that universally for every y, x times y equals 0. What is that x? X equal to 0. When you pick x equal to 0, for any other y that you choose, x times y is equal to 0. Over here, both of those statements are false because 0 isn't in there. 0 is the only element that satisfies x times y equal to 0. You know, one of those x and y's has to be 0. And then here it's true again because both are true because the 0 is in the domain. Okay, so this one is where is a domain that makes that true? Oh, sorry, for which this is true. There's one.
Would it just be 0?
Just 0 by itself. Very good. There exists one particular x in this domain. Well, there's only one thing in the domain, x equal to 0, such that for every y in the domain, what's y going to be? I mean, you picked x equal to 0. Now I got to look at every y. So which ones am I looking at? What are the possibilities for y in this domain?
0.
Just 0. 0 plus 0 is 0. That's the only domain where this works. Right? Not even something like this. D equal to, say, like -1, 0, 1. Or just say -1 and 1. Right? So even this is the only domain that works. Okay, even this one is, even in this one, even with this, that statement is false. Why? Why is it false here?
-1 plus -1 is -2.
Right. Doesn't mean that x and y have to be different. Again, completely literal. We're not implying anything that we're not saying specifically. Unless it's specifically stated, it's not implied. Well, not a priori implied. It might be, but you actually have to prove it. I mean, I didn't say x and y have to be unequal. If I want x and y are unequal, I gotta say so. So, okay, can we make a statement like this that's true? However, you know, with d equal to -1, 1, this statement is true. There exists an x such that for every y, what can I do? Can I add to this about things being unequal? There exists an x such that for every y, something something, and x plus y equals 0. What can I do to fix it?
Could you set a parameter for where y is?
For what? I'm sorry.
For y,
Well, I mean,
I don't know how to say.
why was this false? I mean, this is false over this domain.
Oh, you just cross out can't equal 0.
Can't equal. Well, I mean, this one was false. There exists x such that for every y, x plus y equal to 0. It didn't work because if I chose x equal to -1, I could have y equal to -1 as well. In which case, -1 plus -1 is not 0. Right? It's only because the possibility exists that x is equal to y that makes it false. That's the only trouble with this domain. So how can I fix it? How can I get rid of the possibility that x equals y? I mean, I just need to state it, literally. But how do we state it? How would we state it? There exists an x such that for every y, if...
Can you just put x does not equal y, like the equals with the slash?
And how do I connect? Sure, and how do we connect?
A comma?
Well,
or a semicolon?
You have to use a logical connector.
Implication.
Implication, yeah. There exists an x such that for every y, x not equal to y implies x plus y is equal to 0. Which x could I choose to make this true in this domain?
The negative of y.
Well, there's only two elements in the domain. Which one should I pick? Only two choices. Which one would you like it to be? Here's the domain, here's the statement. So there exists something in the domain that satisfies this statement. Which x do you think would work? Only two choices. Flip a coin.
-1.
X equal to -1, fine. So say that x is -1. Okay, what are the possibilities for y here?
Just
1.
What else? For every y means every y in the domain. So what are the possibilities for y?
1 and -1.
1 and -1. Okay, so x is equal to -1, and y is equal to 1 or -1. Okay, suppose y is equal to 1. Is x not equal to y? Is that true?
Yes.
Yeah. Is this true? X plus y equals 0?
Yes.
Yes. So the implication is true implied.
True.
So the implication is
True.
true. Okay. The other possibility is x equal to -1 and y equal to -1. Is x not equal to y?
No.
False. So the implication is
False.
True.
true.
Because the hypothesis is false.
Yes. The vacuous statement, despite being, somewhat meaningless, is still important. So if you chose x equal to -1, y could be equal to 1 or -1. In one case, the hypothesis is true and the conclusion is true. So the implication is true. The statement is an implication. In the other possibility for y, the hypothesis is false, and I don't care about the conclusion, because when the hypothesis is false, the statement is true. Okay? Again, the vacuous statement, but so that was x equal to -1. What about x equal to 1? Would that work too? Would that give you the same outcome? Would it still be true? For x equal to 1, equal to +1? This is the same kind of analysis. Yeah. Yeah, definitely. You could choose x equal to 1 or -1, and it still works. Right? Because if you chose x equal to 1, right, if x was equal to 1, then y is equal to 1 or -1. So if this is false, the implication is true. Right? If y is equal to 1, this is false. The implication is true. If y is equal to -1, this is true, and that's true. So the implication is true. All right? Don't forget about vacuous statements. So be careful of, we're done anyway, but so be careful to remember false implies whatever is true. So for example, so D is equal to the set of all fish, right? And f of x is equal to x has fur, and y of x is equal to x has teeth. X is a tuna. Okay, so for all x, f x implies, not y, I guess, but 2tx. So within the set of all fish, this statement is what? For all x, x is furry implies x is a tuna. True or false? For all x, x has fur. That's always false. I mean, for all x, x doesn't have fur. So for any x that you pick in the domain, for any fish you pick in the domain, f of x is false. So for every x you pick in the domain, the implication is what?
True.
Yeah. The statement is true. Don't forget about the vacuous statement. It's important. Okay, I mean, this is a cheesy example, but the cheesy examples are important. More about cheesy examples throughout the semester. So more on this next time, and I'll see you on Friday, okay? Email me with any questions or concerns.